So today I'd like to cover sorting. And the reason is we have an exam on, not next week, right? We have one class meeting next week. And then we have the exam on Monday following that. So if we cover sorting today, that means we can review for the exam next week on Wednesday. But before I jump into sorting, maybe some of you have questions about the lab. So I can answer those first if you want. Any questions? No questions. So I'm going to talk about sorting now. And this is the final topic in the class. Look how far. Oh, no, it's not the final topic. Then there's like application programming. That's also. All right, when I do this sorting example, I will do an example. We can use vectors or arrays. Sorting means to take a sequence of values that are not in order, like some numbers or strings, or anything that has what's called an ordering. So we take a sequence of values and we arrange them so that they adhere to an order. They're either increasing or decreasing. And the ordering is defined by that less than operator. So we can work with arrays and see how to work with sorting using an array, or we can work with vectors. What should I use?
Vectors.
How many want to see vectors? How many want to see arrays? Because of vectors. Right. Vectors are easier. So thank you for making that choice. So we're going to have a function. Let me see. In the lab, there's a lab about this. My sort. That's what I just wanted to check that out. Actually, here, we'll just use that function signature right there. So this function takes a reference to a vector, the vector of int, and rearranges the elements in V so that they are in order, in increasing order. But we could do it in decreasing order as well. And then it returns those. And that means the function operates on a reference. That's why we don't pass in a copy. So we don't do this. If we passed in a copy, then we would sort the copy, and then when we return from the function, we would just discard the copy. So that's not going to work. We need to obtain a reference to the vector, not make a copy of the vector, so that we can permanently change this thing that's being passed in as an argument to us. So we create some test data. Let's start by writing the test code. And when we write the test code, it'll be more clear what this mySort function needs to do. I call it mySort because in the standard library there is a routine called sort, and I don't want to have a naming conflict with that. So I call it V here, but once again, these V's are in different scope. All right. I just think it's convenient to use the same letter, but some people think that's confusing, so we could have used U here if we wanted to. It would be the same thing. And then we would put U here. And this, what happens inside this vector is all relative to this name. You know, we are going to end up passing in U. I'll do it like this today. So u dot pushback. Let's push back, say a 3. And let's put 5, maybe 7 values on there. And make this 12. Make this -4. Make this 30. Make that 1. Make that 0. Make this, I don't know, 7. So there's some values. That means when we're done this, let's take a look at it. I'm gonna call it print. I'm gonna print the vector v. So let's have a function that prints the values of the vector. So this is print. That's a good point, right? Do we need to say print u? No, we don't.
You get
In your
some-
main function.
Huh? It doesn't have to be the same. You're in different scope. That's what I'm trying. That's the point I'm trying to make. That this, whatever this is called,
No,
when
you're
you,
in your main function.
oh. I am so stupid. Nobody's stupid in this class. All right, so we print u, and I is less than v dot size. And we'll just do C out V. Oh, so I'm getting confused. I was going to put U there.
You didn't include the vector.
Oh, there it is. Got it. You were faster than the compiler. Really? I ran the compiler, then you said that.
Sorry.
That's amazing. Humans are still faster than computers. Is that true?
When they observe it beforehand.
In some cases. All right, let's see. All tests passed. Oh, you know what? I don't like this. I'm going to put a C out right there. We're not really running any tests, though. We'll create tests for that. But first, we're just going to look at it. So you can see that these are the values. They're not in order. So we want to print. We want to rearrange those so it's -4, 0, 1, 3, 7, 12, 30, like that. All right. So we'll call my sort u. And then we'll print again. And so we're going to do visual inspection, and then we'll change it into tests. And sometimes it's helpful to do visual inspection. All right, so we're not sorting yet. How do we rearrange the order, the elements of V? Well, I want to say that, well, let me discuss that first, what that looks like. So these are the numbers. So what we're going to do, well, this is how I'm going to do it. There's different ways to sort, by the way. And some ways are more efficient than others. But the efficient methods of sorting are complicated. And so we're going to start by learning a simple method of sorting. And we will not cover the complicated method because you'll cover that later, maybe next quarter for those who go on. So to rearrange these, here's the process we're going to use. We're going to set this, this marker here, an index, and it's going to start in position 0. So remember, that is position 0. And we're going to say that we want to scan all of the values following there. We're going to use another index. We're going to let J, maybe it's like this. I need space. We're going to set I and J both to that first spot there. And then what we're going to do, well, let me start like this. I got to get this right. We're going to start in position 0, and then we're going to look at every number and look for the biggest number that we can find. We start with 3. We say, okay, 3 is the biggest number we have. All right, let's go to the next one. Oh, 12. 12 is bigger than 3, so I change my mental note. 12 is the biggest number we have. Look at the next one. Oh, this is not bigger than 12. Look at the next one. 30. Oh, we got a new bigger number. So I'm going to discard the 12 and say, oh, now the biggest number that we have is 30. I'm going to look at the next one. 1, that's less than 30. 0, that's less than 30. 7, that's less than 30. Oh, 30 is the biggest number. And so what I'll do there is I'm going to swap the value that's in slot 1, slot 0, with the value that's in slot 3. I better put the slot numbers in there. That's slot 0, position 0, position 1, position 2, position 3, position 4, position 5. So these are the position indices, see? And I doesn't equal 30, I equals 0. I is a variable that represents an index. And those are so that value is used to reference these positions. So after that process, and we scan to the right, and we swap 30 with 3, that means we have, oh, this is decreasing sequence, right? Do we want to do a decreasing or increasing?
Increasing.
Huh?
Increasing.
It doesn't matter, right?
Yeah,
What's the lab say?
increasing, I believe.
Lab says increasing, right? So let's do decreasing. So you guys get to think about it a little bit. All right. So we got the largest value in this first slot, and we know there's no other value that's bigger than that. So then we advance I, and we do the whole thing all over again. And we say, all right, let's start with 12. 12 is the biggest value we've seen so far. Minus 4 is less than 12. 3 is less than 12. 1 is less than 12. 0 is less than 12. 7 is less than 12. 12 is it. 12 is what we're going to put in the second slot. It's the second largest value. And now we advance I again, and we say we're going to do it all over again. Let's start with minus 4. This is already done. We forget about that. We're just going to the right. So we start with minus 4 and say, all right, we got minus 4. Oh, 3 is bigger than minus 4. So I'll make a mental note. 3 is the biggest value we've seen so far. 1 is less than 3. 0 is less than 3. 7 is bigger than 3. And 7 7 belongs in position 2 or slot 3. I know it's confusing. So we're going to swap what's in this last position with what's in this position 2. So it's 7 and minus 4. Now everything from I to the left, everything at I and less than I, all those positions, those values are in their final position. That's where they're going to stay. We need to keep moving to the right and performing this same process again. Each time we're finding the biggest number from a progressively, shrinking. We're finding the biggest number from a shrinking range. 3, 1, 0, minus 4. Well, 3 is the biggest number, so I don't have to do anything. 1, 0, minus 4, that's already good. 1 is the biggest number. 0 minus 4, 0 is the biggest number. Actually, the example's not that good, right? Because we only had to do 2 swaps. Oh no, 3. Yeah, 2 swaps. All we had to do were 2 swaps to put the vector in the sorted order. Maybe that's not a good example. Anyway, that's what we have there, okay? So how are we going to code that? Well, let's start. We know we need I in a loop. V, confused, shouldn't use the U. There's I. There's the I that we're talking about. And for each I want to find the biggest value starting from I at I or after, something like that. And swap it with the value at I. Exchange it. So now the problem is how to do that. Find the biggest value starting from I. So that means we have to scan from I, starting at I, we're going to scan to the right. In the very beginning of the algorithm, I starts at 0, and that means we have to look at positions 1, 2, 3, 4, 5, 6. And the next pass, I goes to position 1, and now we scan across, 1, 2, 3, 4, 5, 6, and then 2, 3, 4, 5, 6, and then 3, 4, 5, 6. Do you see that? These scans, for each I, we have to do a scan, another scan. When I is a scan across all of V. And then for each value of I, we have to do this little scan. So that's another loop.
Thank you.
So we're going to use J for that. I and J. That should come after this comment. That should come after the comment. And actually, if you don't mind, I want to get rid of this comment. Is it anybody opposed to that? That was temporary. It's a little easier for me, and I'm assuming it's easier for you after you digest that this is what we're doing here. So we know what I is doing. And we're using J to scan starting at, oh, this is wrong, right? What's wrong about this? We got to start at where?
Start at 1.
Huh?
You want to start at 1?
No, we don't start at 1. Huh?
You want to start at I.
We start at I.
Then you go to V dot size minus I.
Um,
No, you want to go to v dot size.
This is okay. This is good. We want to go to the end. So we want to go to the end. So v dot size is where we want to go. But the outer loop, maybe we want to go to v dot size minus 1. Because we don't need, after I, here I, right now, see this I? This is position v dot size minus 1, right here that I have highlighted. Do we need to execute this inner loop when I is on the last element? No. So we can quit when this means I is on the last element, what I have highlighted there. So we can quit here. Now if we didn't, let's suppose that we left it at just v dot size. If we just left it like this, well, I know where this is going. It won't be a problem because j will be set to, in this particular case when I is 6, j will be initialized to 6, and we're okay because we'll end up, just doing nothing, you'll see. So it doesn't matter. This actually doesn't matter. And maybe you can't see it yet, but we'll see it when we figure out what we need to do here, okay? So it doesn't matter if you go to the end or one before the end with I. So when we're scanning across the vector, oops. When we're scanning across the vector, and let's see, I shouldn't have deleted all of those. There we go. At a given point, I'll just do it here. So at some point in the process, I is somewhere in the middle there, right? That's the typical case. We're not going to consider I at the front or I at the end. This is the typical case where I is somewhere inside the vector, not at one of the extremes. Let's suppose that I is here. We've already done this swap, and we're in the middle of this algorithm. And we've done one swap already, and this is the current state of the vector, which is different. See, we swapped 3 and 30. We swapped what was in position 0 with what was in position 3. We swapped those values that were in those two positions. Okay, so we did that already, and this is the result. And then we advanced to the second position, and we saw that 12 was the biggest, so we did nothing, and then we advanced to the third position, position 2, and let's stop there. This is where we're going to think about how to write the code. So we need to, so I is here. Now J does follow. J is going to start here, and then we're going to move J to there, and move J to there, and move J to there, and then move J to there. What do we do for each value of J here? Actually, we can start J there. If we do that, then we have to use this. We start J there. If we start J there, then we got to make sure we don't go one past the end. So we got to use a -1 there. But we don't have to do that. Maybe we'll just keep it simple by not doing that. We'll just start J at I. Let's do it like that. Let's see if we can. Because there's many, many different ways of solving the problem. Many. I'm just showing you one way. And even this one way, there's so many different ways to write the code. So I'm going to try to make it as simple as possible. So before we start scanning J across this vector, this subsequence, I should call it, we're gonna define another integer k, and we'll set that to I. And k is the marker that points to the biggest value that we've seen so far. K points to the biggest value we've seen so far. So the biggest value we've seen so far, we've only seen one thing, -4. Remember, this is the biggest value. This is relative to I here. So when we have this loop on the inside, and we can start at I plus 1. We can do that. Because we already set k to I, so we don't need to look at j equaling I. So -4 is the biggest value we've seen so far. And so we can start with j being 1 past I. And I'm starting to lose people now. I just feel bad. All right, so what do we do? K is a marker. It's the biggest value we've seen so far. The biggest value we've seen so far is -4. That's it. Now let's look at another value. Let's look at 3. So if v of j, right, that's v of j. 3 is v of j. If v of j is bigger than v of k, it means that we found a value that's bigger than the one at k. So what do? We update k. We said we found a new bigger value. K has got to point to the biggest value we've seen so far. So if we found a new value, bigger value, we're going to adjust k to point to it. And when we're done that process, oh here, let's just go through this first before we do that. Let's suppose that j is at index 3. And we're comparing v of j, which is 3, with v of k, which is -4. So v of j is bigger. V of j is bigger than v of k. And therefore, k is set to j. So we're going to move k to j because 3 is the new biggest value. Okay, we adjusted k. Now we're going to advance j. We're in the loop. Is v of j bigger than v of k?
No.
Let's see, v of j is 1. V of k is 3. So v of j is not bigger than v of k. So k is good where it is. Let's leave it alone. Let's advance j again. Is v of j bigger than v of k? No. V of j is 0, v of k is 3. Let's advance j again. Is v of j bigger than v of k?
Yes.
Yeah. So that means we set k to j. Now we're done. We finish. Now when we advance, we actually do advance j. We increment j here. But now the loop condition is false because j now equals v dot size. J is no longer strictly less than v dot size. So when j goes past the end, or goes past the end, then we're finished with the loop. And what do we do when we're finished with the loop, this inner loop?
Go back to the outer loop.
Huh?
Go back to the outer loop.
Go back to?
The first loop.
No, not yet. We got to do something else before. We're going to do that. We're going to go back to the outer loop. But we got to do something before we get there. Swap.
VK equals VI.
Yeah, that's it. VK and VI have to get swapped. So VK and VI.
Swap
There-
the interval.
There actually is a swap function. I think this is going to compile. Let's see. Actually, let's run it. It worked. I pretended to be surprised. There is a swap function. But let's suppose you didn't know there was a swap function. How do you swap the value at v of k with the value at v of I?
You have to call the rate point.
You got to create a temporary value.
Yeah.
We're going to call it t for temporary, or temp. And we're going to copy what's in v of k into temp. So now we can take what's in v of I and copy it into v of k. I'm sorry. Did the same thing. See, I and k right next to each other. So we need to copy what's at I to the kth position. So we do that there, but before we do that, we need to preserve what's in the kth position, so that after we do that copy, we can then lose what's at the ith position by writing into it the temporary from the temporary variable. So these three lines are how to do a swap. You need a third argument. Just imagine this. Imagine you have a cup of tea and a glass of milk. Oh, no. Actually, you accidentally put the tea in the cup and the milk in the, well, you put the tea in the glass and you put the milk in the cup, and you say, no, that's not right. I want to swap these. I want to pour the milk from my teacup into the glass and pour the tea that's in the glass into my teacup. So how do I do that? So you see, I can't do it with two vessels. You need a third vessel. So I'll take the milk that's in my teacup and pour it into that third vessel. And now I can do this. Put this down, and I get my third vessel and fill. Do you see how that works? So that's how to do a swap. You need a third argument, a third variable. Oh, let's check that if that works. There we go. But this is a little easier, so you can use this.
Swap from the vector library.
You know, you might need to include a header file for that. I don't know if swap is not defined here, then you'll need some header file.
C standard.
Maybe. Swap function. It's in, it's in utility in the new one, and the old version, C++ 98, they put it in algorithm. C++ 11, they put it in utility. So which compiler are we using? Which version? This is not a compiler. This is a specification for the language. And this is C++ 98, 1998. This is C++ 11. So you would either include algorithm or include utility, depending on your compiler. Well, here we didn't need it because it's probably included through vector. Probably include through the vector class. But different compilers will do it differently. The specification requires that the function be defined in these headers, depending on the version of the language. And then your compilers will do it slightly differently. So you've got to pay attention to that. All right, so that's it. That's how you do sort. That's not bad, right? There's another let me show you another variation here. Here's another variation. Now, these sorting algorithms have different names, and this one, I think this is called insertion sort, but I don't remember. And there's just too many little names. There's selection sort, there's bubble sort, there's, well, of course, merge sort, and quick sort. That's the one that's generally used, is quick sort, and there's a whole bunch of them, so they're all given names. But I want to show you a variation of this one here, and that is that we don't use a variable k. Get rid of k. And when we find what we do there is we compare v of j with what's at v of I. And if we find a value at j that's bigger than what's at I, then we swap v of I with v of j. I got to say, do we start here? V of j. Yeah, we do. It's the same thing. That's simpler, isn't it? We don't need that. The only thing, it's a little slower because we're doing a swap instead of just setting k.
It'll run longer.
It's slightly slower.
It'll run longer because you're doing more switches.
Exactly, to run it longer, but it's not that costly. It's not that costly. And let's check that we did it right. We did. So which one do you prefer? The fast one or the one that's a tiny bit slower and you'll never notice it, actually?
The tiny bit slower.
Huh?
The tiny bit slower.
Everyone agrees? You like this one better?
I do.
Is that the one you want to memorize for the test? This is on the exam. It's either in an array form, or it's a vector form, or it asks for increasing or decreasing. So it's either going to be arrays or vectors. It'll be either increasing or decreasing. There's 4 variations that I'm going to ask. I'm going to pick from that pool of 4 variations. And then you'll need to write this down on the exam. This would be what you write. You don't have to do the test code or anything like that. This is what you need to know. Yeah.
This isn't until the final exam, though, right?
This exam 3. This will appear on exam 3. It's a week from Monday.
Okay, because lab 8's not till after exam
Oh, no,
3.
no. This is not on exam 3.
Yeah.
Sorry. This
Because
will.
exam 3 doesn't come until-
Binary search is on exam 3. Sorting does not appear on exam 3. Sorting appears on the final. I will ask you on the final to write down a sorting algorithm for me. All right? So you're right. This is not on exam 3. Thank you. Thanks for that. Now, let's take a look at what the test code might look like here. Instead of calling print, we don't want to do visual inspection. We want to write an automated test that does that automates the check for us. And so you know what you do when you develop software is you write these automated tests, and as you develop the system and move forward, you save all of your tests and you run them as a bank of tests. Because it's very common that as you move forward in your project, a bug gets introduced and it breaks some code that you wrote earlier. So you want to preserve all of the tests that you've written and run them all in bulk at iterations in your project. So you see, and that's called regression testing. So you want to run all of your old tests repeatedly as you move into the into the future and add code to see if you've broken something. Something in the past, something you wrote in the past may be working with your system, but then as the system evolves, that old code may not work correctly anymore. So we want to keep the tests. So let's write automated tests here. So after we sort U, and I have to remember it's a U, then we just have to check that what appears in position 0 is 30. And then we got to just go down the list here. I don't think there is a position 7. So it was 30, then 12, then 7, then was it 3? And then 1, 0, and -4. Up. We need a header file for Csusb. Looks good. So there we have it. We've got our automated test. And that's not bad. We could add other tests and test it further, but that's it. Look at all the time we have left. Oh, this. Oh, we should talk about this. Let's look at exercise 2. I want to take a look at this, so you'll do this later. Create 2 programs in a file called slow.cpp and fast.cpp. In slow.cpp, generate a random vector of size 100,000, pass it to your sorting algorithm. Run the program and observe that it never ends. Press Control-C to terminate the process. All right, let's try that. This is our sorting algorithm. Now this is a simple algorithm to understand, and unfortunately, it is slower than a faster, more complicated algorithm. So what we want to do is create a test, or not a test, but it is a test. We want to add 100,000 integers to this vector. So we'll need a loop for that. $100 to 30,000. So we got to push back some random integer. There it is right there. Just to make the integers, we're going to dump the integers. I guess we can do it like that. We'll just leave it like that. And then we call sort. And then we print all tests passed. That looks right. That's what we're asking in that exercise, right?
Mm-hmm.
All right. Let's run slow. It's running. Let's change it so we have 10,000 integers instead of 100,000. We're going to take off a 0 right there. See that? Control-C to kill that. So compile again. Now let's run it with 10,000 integers. How long do you think it's going to take? Take a guess.
Slow.
Huh?
Slow.
Slow?
A little bit slow. A little bit faster.
I think it's gonna finish before I release the return key. Oh, almost. That's like a second. Look how fast it is. That's how the problem is what I call it complexity. This loop here, the number of times, see this condition right here where we're comparing v of j with v of I? How many times does that thing execute? It turns out that the number of times this if condition is checked is some constant multiple of the size of the vector squared. So as the vector gets larger, the number of iterations of the inner loop blows up. You know, it's quadratic. So if you look at the graph, you know, it looks like this. It blows up. So, you know, a relatively small increase in the size of the vector dramatically increases the number of calculations that have to be done. And so we call that, and then we in the computer science start talking about running time. We say, well, the running time of this algorithm is the order of n squared, where n is the number of items in the sequence. So as n gets large, the number of iterations, the number of steps that have to execute gets very large, grows very large. So the running time is actually, it's some constant times n squared. That's how I'm going to write n squared. So this is a bad sorting algorithm. So it's what we're doing. I think it's called insertion sort, but I'm not sure. Maybe it's called selection sort. And then you have other algorithms like merge sort. That's the easiest to understand of the efficient algorithms. And its running time is a constant multiple of a log of n times n. And this is dramatically smaller than this as n gets large. This log n, you know, is small as n gets large. It's still a problem for large sorts, but anyway, that's that. And that's a topic, by the way, when we study the running times, and this is called the efficiency of algorithms. It's called time complexity, or complexity, because there's storage complexity as well. How much storage does algorithms need when they run as a function of the size of the problem n? And that's a topic in computer science called algorithm analysis. And if you're a computer science major, then you've got to take that class. You know, it's a 400 level class. Everybody in the world has to take that class if you major in computer science. You have to learn this stuff. But here I'm just introducing it to you. You'll learn about this actually in data structures in the third course that we have here. Sequence. All right, so 10,000 is too big. 100,000 is too big. I'm going to set it back to 100,000. Last time I did this, last quarter, it completed. I think it took about a minute. I'll just let that run. I'll start a new virtual window. Let's create fast. Let's do it faster. Let's use an efficient algorithm. And actually, the sort that's being used, I think it's quick sort. I would guess that's what the system is using. And this is the time complexity on average. For certain weird cases, you can get n squared, but it statistically doesn't happen enough to worry about it for completely random data. So we're going to assume completely random data. And now instead of calling our sort routine, we're going to call the sort routine in the standard library. Where is that routine?
Algorithms, I think.
Algorithms, yeah. It's in algorithms, but yeah, algorithm. It's defined in algorithm. I think I don't need it here. I think my compiler doesn't require that include. But I believe that in the labs you need that. So the sort is defined in the algorithm header. But we can't call it like that. It's hard to read this. I'm not going to get into those details. You'll learn this in data structures. When you call sort, you have to give a start and an end position. And for this problem, it looks like this. I'll make that a U. U.begin is a reference to the first location. And U.end is one past the end of the vector. And that's how you would run sort. So you can call it with subsequences inside the U. That's the benefit of having that in 2 arguments. Look, slow finish. See that? It wasn't that slow, was it? I'm going to make it really slow. Let's make it 200,000. Maybe it'll break. Let's compile slow. You know, I want slow to really, really be slow. Okay, 200,000. I don't think that's going to finish. And now we're back here to fast. Does everyone agree? We have, oh, that's 200,000. Sorry, I just modified fast, not slow. This is slow, right? Let's make that 200,000. Hope I don't run out of memory. All right, there's slow running with 200,000 items. Here's fast with 200,000 items. I'm going to write that. Now let's compile fast. And let's run fast. But before I run it, let's take a look. Like slow is running. Slow is still running. Here's fast. How fast is it going to run?
Really cool.
Huh?
A second.
Second.
1 second.
Whoa, that's faster than a second. 200,000 items. Look at the difference. Do you see the difference? Is that amazing? That's the difference between this and that. That's a big difference. It's the same, and here's slow. We're going to run, you know, you're going to leave. We're going to finish the classes. Isn't going to run. I don't think this will terminate today. I may be wrong. I don't know. So that's it. And that's kind of what you need to do here is to do that stuff. All right, investigate that. Any questions? Any questions about the lab or the exam or anything like that? We meet once next week on Wednesday. And then the exam is on the Monday following that. That's it then. Okay.